Thank you. This is a joint work with Nicola Chasabianchi and Csaba Sipisvari. And I'll talk about Gibbs-ERM principle, and first I'll set up some notation. So this is a standard parametric setting of of learning, of statistical learning. We have a training set. The parameter space is going to be Euclidean space, and the goal is here is to select hypotheses that minimize the population risk with respect to some loss function, which is not necessarily convex, but it's bounded. And typically what one does is empirical risk minimization, maybe penalized, where empirical risk is defined like this. But in this talk, I will focus on the randomized version of ERM, which is known as Gibbs-ERM principle. And the idea is that instead of doing minimization of the empirical risk, explicitly you sample from a Gibbs distribution whose potential is this regularized empirical risk, and obviously sometimes you're going to select hypotheses which are not minimizers, but perhaps fall not too far from it, which are in high probability concentrated around the minima. And why would we care about such formalism? Well, it arises in a number of interesting areas. For example, this can be seen as an idealized model of stochastic optimization. And in fact, if you look at this stochastic gradient, the Langevin recursion, it's a discrete time process which tracks a diffusion process which mixes and the stationary distribution of whose is the Gibbs distribution, of course under appropriate conditions. And some people also believe that if you run SGD for a long enough time, this roughly Gibbs gives you an intuition of what is going on also in that case. Gibbs-ERM principle also has a connection to Peg-Bayesian analysis. If you're familiar with the Peg-Bayesian analysis, then if you minimize Peg-Bayesian bound, it will give you a Gibbs predictor. And in this talk, I would like to we would like to understand the excess risk of the Gibbs-ERM principle, or the approximation property with respect to the minimizer of the population risk. And such results were known before, but particular interest here is on the bounds which show the interaction between the data distribution and the loss. So for some problems, this interaction might be nice, and then we recover, and then we see that the excess risk is is controlled in a nice way, and the loss, and we assume that the loss is twice differentiable, but possibly non-convex. And there are some regularity assumptions that in the vicinity of the minimizer, the objective function, the curvature of the objective function doesn't change too quickly. So locally Lipschitz Hessian assumption. So the first type of the excess risk I look at in this talk is localized. It's localized within the minimizer, and it tells us basically what is the excess risk of the Gibbs predictor in the Deakin ellipsoid. And what you can say in a distribution dependent fashion, and what you can say, you can say that this excess risk is controlled by the effective dimension, or the soft rank of the problem. So for the low rank problems, or approximately low rank problems, you get bound which is much tighter than some are tighter than some of the previous bounds, which depend on the ambient dimension of the problem. Right. So this analysis also goes through for unregularized case. If I send lambda to 0, I will see that things depend on the rank of the hash in this case. Now, this analysis can also appears occasionally. This quantity also occasionally appears in the analysis of the ridge regression. So this is sort of a you can also see it as an extension to possibly non-convex problems in the case of Gibbs. An interesting case is a generalization of this to the global to the analysis of the global excess risk. And here we are not competing against a single minimizer. We are competing against the distribution of minima, which is given by the relative probability of the Deakin ellipsoids. And to understand the intuition behind this, it's interesting to look at the limiting distribution at the 0 temperature. Which is given by the essentially relative volume of the ellipsoids at the minima. So Gibbs spends more time in the minima of a larger volume, and the bound for the global excess risk is quite similar, but instead of the effective dimension or this notion of the soft rank. Now we have an average soft rank, which is averaged over all the minima, according to this relative distribution. What we pay for this global analysis is the probability of this calligraphic C star, which is the probability of the complement is a probability to be outside of any minimum. And this is well controlled. So this is it's decaying exponentially quickly as gamma increases or temperature, and it does indeed for appropriate tuning of the bound. So the take-home message of this is that first of all, these accessories bounds are characterized in terms of some distribution-dependent quantity, which shows interaction between the loss and the distribution, compared to previous results, which are pessimistic in a sense because they depend on the ambient dimension. And I guess the intuition which you can carry out from this is that low rank minima implies a smaller excess risk, which is perhaps a computational trade-off, because if you think about the first-order optimization algorithms, then problems which are not well conditioned become harder. So there is this inherent trade-off. I guess that's it. In non-convex settings, this is it's analysis of the statistical property, but I guess for nice non-convex problems, sampling and also Langevin algorithm can be not too bad. Computationally, it should be polynomial in the relevant quantities, but yeah, worst case analysis is exponential in D, so it's it depends, I guess.